All right. So good afternoon again. So, all right. So we're gonna do a few of the functions questions from the topics that we did yesterday, from the aspects of it that we covered yesterday. And then we want to look at direct and inverse variation, and what that means, and how we approach questions. And it's a topic that they set a lot of questions on in exam. The direct and inverse variation tend to pop up a lot in exams these days. So you want to be able to know. You want to be able to do these questions. All right. You want to know how to do these questions. And very, very easy. Very, very easy. Trust me. All right. So so these are some of the questions. That's the variations. These are some of the questions from yesterday. So I'm just gonna pick a few of them, do them just to get a chance to practice what we did yesterday, and then I'll move on to the variations. All right. So let's go like that. So let me decide which one we're doing. So remember, the topics that we did was one, using the inverse function to solve the equation. We did when a function is undefined, right? We did how we break a composite function into two simple functions, and then we did inverse of a composite function. So that's what we covered yesterday, and we said that these were like special functions questions that they don't set very often in exams. All right, so we're gonna do a few of these questions, and we don't have to do them in any particular order to cover what we did yesterday. All right, so I'm just looking through to see which one we can maybe. So let's do this one first. Let us do this one right here first. All right, and my aim for doing that one is to cover this thing, and the function is undefined. That's the reason I'm doing this one. All right, I'm going to do the entire question, but our purpose of doing that question is mainly for part B. All right, so let me bring up I want us to do it here. Okay, so doing that question that I've marked there, question that says page 35. So give us two functions, f and g. So f of x is 3 minus x, and g of x is x plus 2 divided by x minus 1, x minus 5. Two functions. First part wants us to calculate g of 2. So g of 2 simply means we put 2 in this g function over here. Simple as that. And so that becomes 2 plus 2 divided by 2 minus 3. As this x that was here and here, those x's are replaced with 2 in the calculation. All right, starting nice and easy. So this becomes 4 divided by negative 1, which then is negative 4. Good. Then part B now. Part B is saying we have to state the value of x for which g of x is undefined. So that means we want when g of x is equal to infinity. That's a way of writing that it is undefined. This is a symbol for undefined. And g of x, remember, is x plus 2 divided by x minus 5. And that becomes undefined when this denominator becomes equal to 0. That's when it becomes undefined.
Sir, for A, isn't it 2 minus 5?
Huh?
For A, isn't it 2 minus 5?
Yeah, my mistake. 2 minus 5, not 3. All right, 2 minus 5. So this is negative 3. And so it's that answer. All right, thanks for that. -4/3. All right, good. All right, so back to this question. So it's when the denominator is equal to 0. So g of x is undefined when the denominator is equal to 0. So we can state that g of x is undefined. G of x is undefined when the denominator, which is x minus 5, is equal to 0, i.e., if you transpose a -5, it becomes +5, and x is equal to 5. And that is your answer right here. It's easy as that. This was the answer for part A up here. That is the answer for part B right there. All right. So that was the undefined business. Simple as that. If they wanted when g of x is equal to 0, let's say they put in another part and so when g of x is equal to 0, which I didn't ask you. All right. So when g of x is equal to 0, that is when the x plus 2 divided by the x minus 5 is equal to 0. So you'll see that if you were to multiply this denominator across here, then you would end up with x plus 2 equals 0, which really is saying that the numerator is equal to 0, because the 0 times this thing that we multiply up here is going to keep the right hand side as 0 anyway. All right, so a fraction is 0 when the numerator is 0, and that is therefore when x is -2. So g of x is 0 when x is -2. So that is just to emphasize the point that undefined does not mean 0. When a fraction is undefined, the denominator is 0. When a fraction is 0, the numerator is 0. All right? The numerator is 0. That is that. All right. Part C. Part C. We're just completing the question now. So part C is first to find g of f of x. All right. So g of f means f into g. Remember, it means f into g. So let's look at the f and the g up here. It means that we're taking this, we're bringing it here, and we're also taking it there. All right, so we're going to replace the x in those two places. That's what we're doing. All right, so let me erase that again. Good, so we're going to form it here now. So put in the g, we put in the f into the g. When we put f into the g, it becomes, where the x is, it becomes 3 minus x plus 2 over 3 minus x minus 5. And we can simplify it. If you don't understand, let me know, guys. All right, and then when we break this out, the 3 and the 2 is 5. So that becomes 5 minus x. This is a minus x here. Divided by 3 minus 5 is -2. 3 minus 5 is -2. And then this negative x comes back again right here. How can I leave it like that? That is g of f. All right. And then we come back. We come back to d, which is first to find f to the minus 1 of 4. To find f to the minus 1 of 4, we're going to find f to the minus 1 of x first. And then we substitute the 4 to get f to the minus 1 of 4. All right, so let's do it now. So we're going to start by saying f equals 3 minus x. And the funny thing about this function that the inverse is also going to be f minus x, and that is possible for a function that's inverse to be the same thing. All right. I won't bother to explain. I can maybe show you, but I won't bother. I can show you still. I can show you why that is so. So that when we form the inverse, the f becomes x, it becomes 3 minus the x becomes f to the minus 1. So if we transpose this over here and take the x over here, you see that you basically get by the same function that you had before. You get back f to the minus 1 equals 3 minus x as well. So this up here is the inverse, this up here is a function. This is a function. And this down here is the inverse. And the two of them basically have the same expression, 3 minus x, 3 minus x. I might wonder, how is that possible? All right. But let us do the f to the minus 1 of 4 first, and I explain to you why that is possible. So we can put the matter of x, and then we can say therefore, I put in the 4 now. F to the minus 1 of 4 is 3 minus 4, which is negative 1. That is negative 1. All right, now let me show you why the f and the f to the minus 1 is the same now. I'm going to show you on a sketch. Remember, there are reflections of each other in the line y equals x, right? So if I were to draw like a sketch of that graph, y-axis, x-axis. Now the line, the function f equals 3 minus x is a line that basically goes like this. Right? It crosses the y-axis at 3, x-axis at 3, and crosses the y-axis at 3. You can test it if you want. Remember, this is the same as y equals 3 minus x. You know? The same thing. And on the x-axis, the y value is 0. So if you put right here, the y value is 0. And so 0 will be equal to 3 minus x. And so x will be equal to 3. So this 3 is correct. And at this point, the x value is 0. So you put x value equals 0 in this, you're going to get y equals 3. So that shows that it cuts the y-axis at 3 and also cuts the x-axis at 3. And when we do coordinate geometry, you'll be able to see that a little bit quicker with me not having to worry at all. All right? So just explaining it now, but we do coordinate geometry at a topic, which is our next topic actually, you'll see that is the case. Now, that is the line. So this function is f function. Right now, this is the f function. Remember, the relationship between a function and its inverse is a reflection line y equals x. So, if I draw the line y equals x, which is right down the middle, like that, y equals x, right? Then this will be perpendicular to that, right? And this length will be equal to this length, all right? And you see that if you reflect this point, it's coming right back to here. And if you reflect this point, it's going right back to there. And so, in fact, any point on this line, any point on this side you reflect is going to the same distance on this side, just as those 2 points, the 3 and the 3. And that is why those two functions are the same exact line. So if I were to draw the inverse, it would basically be the same line. If I were to draw the inverse, it would be the same exact line. Same exact line. So the function and its inverse would be the same line. Let's extend this black section down here and extend this blue section up here. All right. And this part is f to the minus 1, the same function. So the function and its inverse is the same line in this example. Simply because this line has a gradient of -1 and this line has a gradient of 1. But don't worry about it just now, why that is so. When the gradient of a line is -1, then it and its image, it and its inverse end up to be being the same line. All right. So that's just a little explanation why that is so. Just in case you want to know. All right. So that ends that question. All right, so that covers the undefined business. The next, I want to do an example now where someone use the inverse function to solve an equation. So let's look for one of those. We're using the inverse function to solve an equation. I think it's just this first one here now, right here. Right down here, see? You see them say find g to the minus 1 and hence solve that. That is using inverse function to solve the equation. These two right here is the example that we're going to do now to use the inverse function to solve an equation. So let's look at that. So looking at this second question now, which is number 47. So we're doing this one now. All right, I'm going to run through all of it for revision, no problem. All right, let me get the purple. Okay, so they give us two functions again, which is g of x is 2x plus 1, 2x plus 3 divided by x minus 4, which is g of x. And they also gave us h of x, and h of x is just 1 over x divided by x. And the first part wants us to find g of 7. So g of 7 means I put 7 in the g function right there. And so that becomes 2 times 7 plus 3 divided by 7 minus 4. 2 times 7 is 14. 14 and 3 is 17. So numerator is 17 divided by 4 minus, the 7 minus 4 there is 3. So that is 17 over 3. I can leave it like that, no problem. All right, the next part, part 2, wants us to find h of g of x. Remember, h of g of x now means g into h. G into h. All right, so it means that we are putting all of g into h right here. That is our form by composite function. All right, so that becomes 1 divided by all of g, 2x plus 3 divided by x minus 4. When you divide that by a fraction, you can invert and multiply. Everybody remembers that. When you divide by a fraction, you can invert and multiply. So this really becomes 1 times x minus 4 divided by 2x plus 3. Could have written it as this as my answer, but I'm going step by step. All right, reciprocal of a fraction. This is reciprocal of the fraction, which means you just flip this around, just flip this over as a result, which is what this works out to be. X minus 4 over 2x plus 3. All right, let's go step by step with you guys now. Okay, good. And then that is part 2. And then we'll come to part 3 and 4 now, which is where I really want us to focus on now, which is using the inverse function to solve the equation. All right, I have to do a question like this in the classwork on Wednesday. All right, so the question firstly, part 3, wants us to find g to the minus 1 of x. That's the inverse function, the one, g to the minus 1 of x. So we're going to start as usual by saying g equals 2x plus 3 divided by x minus 4. And this is the function. This is the original function. And we want to inverse it. So we're going to inverse it. When we inverse it, the g becomes x. And the x here and here each becomes the range and inverse function, which is written g to the minus 1. So we get 2g to the minus 1 plus 3 divided by g to the minus 1 minus 4. This really now is the inverse now. This is the inverse. But we need to make the g to the minus 1 the subject. All right? We need to make the g to the minus 1 the subject. So what do we do to make the g to the minus 1 the subject when we have this rational function? First, we're going to multiply this entire denominator across here by the x. All right? And when you do that, we're going to end up multiplying the x times this and the x times that. All right, so we're going to get x g to the minus 1 minus 4x equals 2g to the minus 1 plus 3. Then we want to group the terms with g to the minus 1 over onto this side, and this negative 4 we want to take it onto that side. That's a transposition now. All right, I want to group all the terms with g to the minus 1 on the left side. So that's going to become x times g to the minus 1 minus, when this goes over, it becomes a minus. All right, so it becomes minus 2g to the minus 1 equals, this plus 3 remains as plus 3, and then this minus 4x goes over and become positive 4x. And then we can factorize the g to the minus 1 out of those two terms now. So we put g to the minus 1 bracket out of this, it becomes x. Out of this, it becomes negative 2. And that leaves us with 3 plus 4x. And then all we need to do now is divide this down on both sides as one term, one expression. So divide both sides by that expression. And when you do that, you're left with g to the minus 1 equals 3 plus 4x divided by x minus 2. And now that we're finished, we can put back off x. We know that we're finding a function of x. So that is g to the minus 1 of x, which is what they wanted. All right, and see, in this question it says hence alone, hence, not hence or otherwise, hence. Hence means we have to use this to solve that. That's what hence means. All right, so I'm going to part 4. All right, so we're going to say hence if g of x equals 6, using the rule now, we know, then x equals g to the minus 1 of 6. Remember the rule. The rule with f, but it works with anything that is used to represent a function, g or h or k or anything. All right, let's just rewrite the rule that we are using. The rule that we wrote was if f of x equals some value, some number, then x will be equal to f to the minus 1 of that value. Where this is an equation, and we're trying to solve it, meaning we're trying to find x. All right, so that is what we're using. And therefore, we need to find g to the minus 1 of 6. So we need to find. And this is our g to the minus 1 function. So all we have to do is put 6 in there. So this becomes that x equals, put the g to the minus 1 there. I put in, as I said, the 6 in that. And then it's going to be 3 plus 4 times 6 divided by 6 minus 2. That's where the other x is. All right. That's g to the minus 1 of 6. So you put 6 in the g to the minus 1 function. All right. And so x becomes, this is 24. So it's 3 plus 24 over the 4 minus 6 minus 2 is 4. And so that's basically 27 over 4. 27 over 4. All right. Now, so for the question I said otherwise, hence or otherwise. So let's use our otherwise method. So let's use our doing for the otherwise method. Otherwise, if we're doing it the otherwise method, we're solving g of x equals 6. They would have to write what g of x is equal to and equate it to 6. Equate it to 6. The g of x is the same thing that this is. This is g of x. right? Original g of x. So it will be 2x plus 3 divided by x minus 4, and you put in that equals 6. And you're trying to solve that. All right? You're solving it straight. So to be a procedure, you have to multiply this across here first by the 6, right? Multiply that denominator across by the 6, you become 2x plus 3 equals 6 times x first, and then 6 times negative 4. All right? So it will become 6x minus 24. What will we do now? We can carry this 24 over this side and add it and take this 2x over this side and subtract. Alright, it's a shortcut method. So this becomes 6x minus 2x. That's why we carry this over here. And then this minus 25 come over here, become minus 24 goes over there as plus 24. So this 3 is already there. It becomes 3 plus 24. So the left side is 27 equals 6x minus 2x is 4x. Alright, so that becomes 4x. And then to leave x as a subject, I divide under the 4. Divide under the 4. And so the x would be left equal to 27 over 4. Which basically is the same thing we have here. So x equals 27 over 4. But because the question said hence alone, you never say hence or otherwise. We cannot do it this way. If we do it that way, you're not going to get the marks. Because the question only said hence. Alright, and that's what the question in the classwork on Wednesday is going to say. It's not going to say hence or otherwise. It's going to just say hence. So it means that you have to use the inverse function to do it. Alright, so that is that. So we did undefined. We did undefined. We use inverse function to solve the equation. What else we have to do now? We have to split a composite function into two simple functions. So let's do an example with that now. To split a composite function into two simple functions. Alright, so we can use this one. We can use this question down here for that. Alright. And while we do the splitting, I see they give us k of x as a composite function in this question. And I want us to break, they tell us that it is actually g of f. And I want us to break it into those two simple functions. Alright? And then having done that, they want us to do an inverse of a composite function part. So we can cover both parts in, and this is be a proof method. Prove the rule. Prove the inverse of a composite function. So we're doing two things in this topic, in this question. We're doing the break in the composite function, and we're doing inverse of a composite function in this one. And we're doing the prove the rule method. We're going to do another example where we use the rule for the inverse of a composite function, which, let me see if there's any right here. See it here, this is what. I want to do this one next. This one is a user rule. See it here, no? Because it gives us this 2 to find. And then it says hence. Hence or otherwise, we'll use the hence method. Hence find that. Alright, so that will cover the next two things that we want to cover. Alright, so we're going to look at splitting a composite function for this example down here now. So let me erase the one that we're not doing yet. Alright, so the one that is circled there is the one that we're doing now. Alright, so let's go. That's because we want to cover how you split a composite function. So this question says the composite function, see they tell us that it is composite. Composite function k is defined as k of x is 2x minus 1 squared. That's our composite function. Part 1 says express k of x as g of f of x, where f and g are two simple functions. And basically, they want us to find the two simple functions. See that? So they're telling us that k of x is actually g of f of x. That's what they're telling us in part 2. So instead of writing k of x equals this, we can write, so we can say therefore, g of f of x equals 2x minus 1 squared. And then we want to find f of x and want to find g of x. We want to find those two functions. So that's splitting a composite function into two simple functions. What do we say? We say it's a two-steps process. We say you must find the inner function first, which is this one. How we do it? Let the inner function be equal to the expression within. Over here, expression within would be that 2x minus 1. That's our first step. Let the inner function be equal to the expression within. This is the inner function. This is the inner function, and this is what we call the expression within. The expression within. Expression within. So make them equal. I always find the inner function first. All right. So we're gonna say let. That's the procedure we're doing now. Two steps process. Let f of x be equal to the expression within, which is 2x minus 1. And what we'll do next, let's use a different color for what we'll do next. Then you replace the inner function with x. And also replace the expression within with x. That's what you do next. And that's going to leave you with your outer function. So we can say, therefore, I'm going to actually leave it in blue now. Therefore, the g of x, if I replace right here with x, I'm left with g of x. G of this x right here. G of x becomes equal to, when you put x in this place right here, you just get x squared. All right, so we're going to end up with x in the bracket squared. But when it's x alone in the bracket, you don't need to show the bracket. And so it's just x squared. It's just x squared. But understand that? So those are my two simple functions, right, from that composite function. But understand everything so far?
Yes, sir.
So you have one question. All right. Everybody good?
I was going to ask why I put the bracket for the x squared, sir, but
Oh, okay. So I just put it because these two brackets are there. So I just showing somebody we're placing the value inside the bracket there with the x. That's why I put by the bracket. We don't need it in this case because x squared in the bracket without the bracket is the same difference, right? We all understand that. All right. So far so good, guys. So far so good. Very good so far. All right, nice. Okay. So the next part now I want to do with the question is now to show. I remember the show method for the inverse of a composite function is a long method because you have to work out what this side equals, what is equal to, and you also have to work out what this side is equal to. All right, it's a long process. To do this show method, you have to work out the left side and you also have to work out the right side and show that they are the same. Now remember that the k now, the k really is the same as g of f. K is g of f, you know. So when I have k to the minus 1 here, k to the minus 1 here, it's same as saying g of f to the minus 1. The k and the g of f is the same thing. All right, so let us work it over here. All right, so we're going to start with what we have, right, which are those two functions. Let me rewrite them for the next part. So for part two, what we have the f equals 2x minus 1. We're leaving out the of x for the time being. And we have the g equals x squared. All right, we're just trying to simplify it. All right, and what we require to do, we want to show that the k of x, right? Let me write to show that the minus 1 is
Senior.
the minus 1
Senior.
minus 1. Mute the mic, please. Somebody coming on. You need to mute the mic, please. Oh, I'm confused. It's not coming out. Now I'm confused. Alright, I'm looking at this. I'm also looking at this. Alright, let's see. Alright. Okay, good. Right. So that's what we're trying to show. K to the minus 1 is equal to F to the minus 1 of G to the minus 1. So we can say, i.e., that is, we're really trying to show that G of F all to the minus 1. Remember, this G of F inside this K now. So G of F all to the minus 1 is F to the minus 1 of G to the minus 1. That's what we're trying to show. Alright? And we'll show that by working out this side, what it is, and then working out this side and see that it is the same. Alright? That's what the procedure is. Alright, so I want to start by doing the GF r to the minus 1 first. That's what we're going to do. GF r to the minus 1. Remember that the GF is actually what we're given. Right here. And this is the K now, which is also GF. So the theta, the GF is this. Alright, 2x minus 1 all squared. Alright, so the GF really is 2x minus 1 all squared. So I want to inverse that first. That's what we get. So when we inverse this, the GF becomes x, and the x here becomes GF r to the minus 1. I'm going to put a big bracket. So I'm going to put 2 GF r to the minus 1 all squared. What understand that? I replace this x with the GF r to the minus 1. Just as we would with a simple function. We're not doing it with a composite function. Same procedure. And then I want to transpose to make this the subject. So to make that the subject, I need to get rid of the square first. Alright? So we're going to assume that is a positive square root we need. So we're going to square both sides first. And the inverse of square is square root. Alright? So when we square root both sides, we're going to get the square root of x equals 2 GF to the minus 1 minus 1. What understand that? What we did was to square root this side and to square root that side. Right. This square root will wipe out that 2, and then this square root of x comes back here. And that it has nothing to wipe it out or to wipe out. Alright? So that's what we have. And we're trying to make this the subject now. This thing here. This. So we'll make that the subject. Carry over the 1 and add it and then divide under 2. That's what we do to get that as a subject. So carry over the 1, we get the square root of x plus 1 and then divide under 2. That leaves us with GF all to the minus 1. So we have worked out the left side. Let's put it in a red box. So we can just look back at it when we finish and remember what it is. And that is the left side we just worked out. This left side. Now we need to work out the right side. Alright? Alright, so working out the right side now. So let's write what we're working out. So I want to work out now. I want to work out f to the minus 1 of g to the minus 1. That's what we're trying to work out now. Alright? So to get f to the minus 1 of g to the minus 1, we need each of them first. We need the f to the minus 1 and the g to the minus 1. And then we'll composite them. Alright? So ready now. So remember that the f was just this. 2x minus 1. So Let's write that first. The f is 2x minus 1. And let's do the g over this side. And the g is x squared. See there? The g is x squared. Alright? So we're going to inverse this one first. We're going to get x equal 2 f to the minus 1 minus 1. Then we want to leave this as a subject. So what do we do? Carry over the 1 and add it and then divide under 2. Alright, nice and easy. So we're going to get x plus 1. Divide under 2 now. So get over 2 equals f to the minus 1. So we have f to the minus 1. So let's use this and get g to the minus 1 now. So we're going to inverse this. When we inverse that, the g becomes x. And the x here becomes g to the minus 1. So we get g to the minus 1, but it is all squared. So g to the minus 1 all squared. And then now, to get rid of this square, because we want to leave this as a subject, we square root both sides. So we get square root of x equals g to the minus 1. That it is. That is it. We have g to the minus 1 equals this, and we have the f to the minus 1 equals that. And we're really trying to find this f to the minus 1 of g to the minus 1, which really means, what does it mean again? It means, this means g to the minus 1 into f to the minus 1. So it means that we're taking this one, g to the minus 1, and bring it and put it into f to the minus 1 right there to form that composite function. G to the minus 1 into f to the minus 1. So we can write it now. We can say therefore, f to the minus 1 of g to the minus 1 is, remember now, you're going to put this over here. And so it becomes the square root of x, where the x was, put by the plus 1 and divide by the 2. And this now in the box is our f to the minus 1 of g to the minus 1. And then if we compare these two things now, these two things, compare them, see that they're the same. And so I've shown it. We can write our conclusion down here. Right. So therefore, gf all to the minus 1 is equal to f to the minus 1 of g to the minus 1, which actually is the square root of x plus 1 over 2. Remember that this is k, you know. So essentially, we can say i.e. k to the minus 1 is f to the minus 1 of g to the minus 1, which is what it told us to prove right here. All that happens, all that does that mean is that over here, they are putting on the of x expression. Of x. Don't matter whether they put it on or leave it off, don't make a difference. It's the same thing as you can see there. And so this is a shown. This was shown. That is the answer. We have shown that it is true. If you want to put in the of x now, you can put it there. Of x. Of x. If you feel like you want to put it. And that's it. Simple, because remember, the g of f is x. But good. So far so good. And that is a prove the rule method.
Sir,
right. Yeah.
I don't know if it, I'm just a bit tired, but I feel like I got lost and then I'm not exactly sure.
Well, the beauty about it is that we're recording the video. So therefore, what you want to do is just, look back at the video. Since you're not sure, look back at the video and you say you're tired. Look back at the video right? Catch the flow. Remember, you can pause, rewind, start and stop, and so forth. You know, catch a little section. Because this is something we went through yesterday. It's not brand new, right? So I want you to watch the video again later. You know, pause and stop, get some rest, and then get up and watch it. And then you'll see, you know, if you're still missing something, then you link me. We talk. So we
Yes,
can
sir.
clarify. All right?
Yes,
Let's do
sir.
that. All right. All right. So let us go now and do the other one last one, which is to use the rule, which basically is this question up here now. Use the rule example, right? Inverse of a composite function. So we're looking at this question now. Use the rule example, this one. All right, and we're gonna look at the direct and inverse variation. Very easy stuff, trust me, very easy. We'll finish in another hour or less. All right, so they give us those two functions. Let's go quickly. So they give us those two functions, and they are f of x equals 3x minus 5, and g of x equals half x. Half x is the same as x over 2. Same thing. I like to write it as a fraction, so there's no messing up, right? Half x is the same as x over 2. And the first part wants us to find f of negative 3. F of negative 3 means that we'll put in negative 3 in the f function right there. So it becomes 3 times negative 3 minus 5. That is negative 9 minus 5, which is negative 14. Minus 9 and minus 5, negative 14. All right, then we'll come to part B. B part 1 wants us to find f to the minus 1 of x. So we want to find the inverse of this one. So I'm going to start again by saying f equals 3x minus 5. Same procedure, we're going to inverse it. When we inverse it, this becomes x, this becomes 3 times f to the minus 1 minus 5. That's the inverse function. We need to make it the subject. Easy. 3 over the 5 becomes plus 5 and then divide under the 3. You must see it by now. We're doing the same way, doing them the same way all the time. So it's x plus 5 divided by 3, that is f to the minus 1. All right, so we can say i.e. f to the minus 1 is x plus 5 over 3. F to the minus 1 is x plus 5 over 3. And because them give us the of x, we can put it back there so them can see it. So let's put it back. Of x. All right, that's the answer for that part. Then part 2 wants g to the minus 1. So let's go. G to the minus 1. So part 2 wants g to the minus 1. G to the minus 1 of x. That's what they want in part 2. So let's start as usual by saying g equals, and what was g again? G is x over 2. G is x over 2. I'm going to inverse this. Nice and easy. G becomes x, and x becomes g to the minus 1 divided by 2. Right now, you want to leave this as a subject. Easy. Let's multiply the 2 across here. All right, so you get g to the minus 1 equals 2x. Inverse function is 2x. So we can say, i.e., that is g to the minus 1 is 2x. And again, we can put in back of x. So since you wanted the of x, we can give it back to them. Of x. All right, so that's my g to the minus 1 of x. And we'll come to part C now. Part C. Part C. I'm going to just use the hence method. Part C. That's 3. Part C. Part C. Part C says hence or otherwise. We're not going to do the otherwise. We're going to do hence. We're going to do the hence method. We want to find this. So we can write it like this. Hence. What I want us to find? I want us to find g of f all to the minus 1. So you see in this question, the left half the of x, see there? So sometimes I put the of x, sometimes I leave it off. Look off x that would have been here. Left it off. So sometimes I put it, sometimes I leave it off. So it don't make a difference. Right? So we want to do that now. So that means a different color now to show what we have to do. You have to know that this, in terms of these two things, the f to the minus 1 and the g to the minus 1, this thing here, we have to know that it is equal to f to the minus 1. If the f comes second in here, must come first out there. Of g to the minus 1. If the g comes first in here, must come second out there. Right? And so to solve this, all we need to do is work this out. What does this mean? This means, let me write it. It means g to the minus 1 into f to the minus 1. That's what it means. That's what we're going to do. It means this one into this one. All right? And we'll just work it. So what is it? It means that, let's show it on here now. It means that we'll put in this one into this one right there. G to the minus 1 into f to the minus 1. All right? Well, for the blue, the result of that is going to be 2x where the x is, plus 5 divided by 3. And that is the answer. Quick and fast. And I won't bother to do it the long way. All right? To work it out the long way. I can do it quick still enough. Let's just run the otherwise method. That is the hence method. What do you understand so far? Let's just run the otherwise method. Let's do the otherwise method. Otherwise. Otherwise. So otherwise, we're trying to find g of f r to the minus 1, right? To find g of f r to the minus 1, we have to find g of f first and then inverse it. What was the g and the f again? The g is, let's try the f first. The f is 3x minus 5, and the g is x over 2. Half x is x over 2, right? Like that. So doing this, we have to find the g of f first. All right, so we can say now the g of f, which I have to find first, is equal to f into the g. I'm going to mark it for you. Means the f into the g right here. All right, that's what this means, f into g. And that would then become 3x, not that color. Remember for the blue. Right, that would then become 3x minus 5 divided by 2. That will be the g of f. Right? And then we want to inverse it. To get this, we have to now inverse this. All right, so we're going to inverse that now. When we inverse that, the g of f becomes x equals, the x here becomes g of f to the minus 1. So it becomes 3 g of f r to the minus 1. I know you can't write this enough. Can't write that. This and this different. Right? This one means g of f to the minus 1. Different thing. This means the inverse of the composite function g of f, which is different. All right, so you have to bracket it, guys. You have to bracket it and write it the correct way. All right, so ready now. Back to this. I am now inversing this thing, right? Inversing that. So this becomes that, and this becomes that, and I'm putting back the minus 5 divided by 2. And I'm not trying to make this thing the subject to get the inverse, which we know the answer is supposed to be this right here that we just got up there. All right. So what do we do first? What we do first is multiply this 2 across here. Cross multiply the 2. I will multiply both sides by 2. So when we do that, we'll get 2x equals 3GF all to the minus 1 minus 5. To leave this as a subject node, carry over the 5 and then divide under the 3. All right. So it becomes 2x plus 5 divided by 3. That leaves us with GF r to the minus 1. And you see that is the same thing that we got up there. 2x plus 5 over 3. There. 2x plus 5 over 3. All right. That will be the otherwise method. All right, guys. That is it. So you just need to go and watch the video and see this thing again. Let's go look at the direct and inverse variation. Quick and fast, nice and easy. It's so easy we can do it quick. Trust me. All right. So let me save this. All right. So direct and inverse variation now. Okay. Direct and inverse variation.
Excuse me, sir. I have a question.
Yeah.
Um, you know, when you said that when you put the G into the F, it will becomes G negative 1 and F of F negative 1. What if you take out the G from the F? What would it become? Would it remain the same as GF?
If you take out the G, it can't remain the same. If you do something different, you're gonna get something different. That's why you have to put it back exactly as it is. Mathematics is the most exact science. It can't be two different things and be the same thing at the same time. There are exceptions, but exceptions are rare and few. Like for example, how we had the one case where the inverse function and the function was the same. Those are like special cases. Generally speaking, if it is different, it is different. Because mathematics is the most exact science. So if it's going to be so, if the expression is different, the result is different. So f of g will be different from g of f. Fg to the minus 1 will be different from fg all to the minus 1. It's different, right? So let me just bring up something quick and show you. Right. So fg all to the minus 1 is different from fg to the minus 1. Different. It so happens that this thing will always be equal to g to the minus 1 of f to the minus 1. Those two things will always be the same. Or prove it and we use it. And you have to pay attention to the details, and it has to be like that. I use two different letters. I use two different letters like r of s, r to the minus 1. This will always be equal to s to the minus 1 of r to the minus 1. And you realize that the way that you get this is different from the way that you get this. Let's just mention it again. All right? Or we can use the f and the g as example up here. The way that you get this is different from the way that you get this. How do we get this? To get this side, we have to do f of g first, which is a composite. And then after we get f of g, we inverse it in the normal way. That's how we get that side. To get this side, what we have to do? We have to find g to the minus 1, and we have to also find f to the minus 1. And then after we do that, we have to put the f to the minus 1 into the g to the minus 1. That is how we get this one, this side. Two different approaches, but the result will be the same. The final result will be the same. That's just the nature of the inverse of a composite function. All right, just pay attention to the detail. If you have f first in here, it is second out here. And if you have g first in here, second out in here, it is first out here. And it can't change. So if you go and do this, for example, if you go and do this, fg r to the minus 1 and you write f to the minus 1, g to the minus 1. These two things will not be equal. If they are equal, it must be a special case. Generally speaking, they are not equal. So don't even bother do this. Don't do it. Don't do it. If the f come first, you can't put the f first out here. Wrong. It's gonna be wrong. And CSEC is not gonna give you a question where it work out to be the same. Will not give you a question where it work out to be the same. The functions will be such that they are different. You might have a special case when it can be the same. But generally speaking, they have to be this. Has to be this one, right? That answers the question, boss?
Yes, sir.
Good. So pay attention to the details and stick to the details. Don't try play with it. All right? Stick to the details. If I wanted you to have other considerations, I would tell you them. Right? It is as I told you. All right. So I want us now to look at inverse and direct variations. All right? Not this one now. And I'm doing this now because it comes under the functions topic in CSEC. All right, direct and inverse variation. All right. So what is direct and inverse variation? Now, variation has to do with values that are changing, quantities that are changing. Values changing up, down, increasing or decreasing values, increasing or decreasing quantities. That's what this has to do with. And those and it has to do with the relationship between two changing values, two changing quantities, two related quantities that are changing. They can be changing in a direct way, or they can be changing in a, what we call an inverse way. They can have a direct variation, or they can have an inverse variation. Now, let me give you a practical example. So the direct variation is one where as one quantity increases, the other naturally increases as well. Just naturally increases. As one quantity increases, the other one naturally increases. But the inverse variation is one where as one quantity increases, the other decreases. All right. Now let us talk about a simple example. Before I get into it, I want us to look at a simple example. All right. So let me see what's happening here. Don't even know why that thing is on the screen. I don't know why that's on the screen. All right. So let's do a simple example. Think about this now. So let's say that there are men doing a work. Men. A number of men doing a work, doing a job. And let's say that job is that they are making bricks. So there are a number of men. The number of men is M. They are making bricks or blocks. So the men are making blocks. And the number of blocks is B that they make. And they work a number of days. And the number of days is D. So these are quantities that are changing. M is a quantity. M means the number of men. B is a count of the blocks. Number of blocks that are made by the men. And D is the time that it takes, the number of days that it takes to make the blocks. All right? And the number of men can increase or decrease. All right? And also, the number of blocks can increase or decrease. All right? The number of blocks can increase or decrease. And then the number of days, the days is how long they take to finish the work. The number of days that they take to finish the work will now depend on the number of men working, right, for a fixed number of blocks. All right, so let's think about it now. Think about it now. What if I increase the number of men working on the site? So initially I had 50 men working on the site, right? Tell me naturally what will happen if I increase the number of men working on the site. What would happen naturally in a block factory? So somebody just tell me, common sense. If I increase the number of men,
So if you
but double the
increase
number of
the
men,
So if we increase the amount of men, that means the days will decrease.
The days that it take to make the same number of blocks. So
Yes, sir.
the days that it take to make, say, the same number of blocks, say if it's 100 blocks, if I increase the number of men working, then the number of days that it takes to make the same 100 blocks will decrease. So what it means, therefore, is that the number of men and the number of days would have an inverse variation. Because if I increase the number of men, then the number of days taken to finish the same number of blocks will decrease. You understand that? So the number of men and the number of days worked will have an inverse variation. Similarly, if I reduce the number of men working, then it will take a longer time. It will take more days to produce the same number of blocks. So once we fix the number of blocks that is making, right, and keep the number of blocks constant, that's why you must have a variation constant now. There must be some constant in the variation relationship. In this case, the variation constant is the number of blocks. That is what we're talking about. Then if we increase the number of men to get the same constant number, which is 100 blocks, then the number of days will be less, meaning they will take less days. If we decrease the number of men working, right, we're assuming that they're working at the same pace, at the same rate, then the number of days will increase that requires to make the blocks. So more men, less days. Less men, more days. So if the number of blocks constant, then the men and the days have an inverse variation. All right, so those would have an inverse variation. So it's right over here. So men and the days would be inverse. Inverse variation. All right, so let's look at another scenario now. Let's say the number of days they're working now is the same. So let's say the number of days working is the same. So they're working for let's say they're working for 10 days, constant 10 days. They're working for 10 days constant now. So they're working for 10 days and the number of days not increasing. So over 10 days period, if I increase the number of men working in 10 days, what would think would happen with the number of blocks in that same 10 days? What would happen? How many blocks? What would happen to the number of blocks made if I increase the number of men? Somebody tell me now. If I'm keeping the number of days constant, keeping the number of days constant of my variation. So I'm not changing the number of men work, the number of days that they're working. They're working 10 days, fixed 10 days. But I double the number of men working in the same 10 days, double it. What do you think would happen to the number of blocks produced?
You get more blocks. That number would be double.
Exactly, you get more blocks. And what happens if I reduce the number of men working?
You get less blocks.
Less blocks. So in that case, when the number of men increases, the number of blocks increases. And when the number of men decreases, the number of blocks decreases. So these two now would have a direct variation if this is my constant. So that's how inverse and direct variation work. When if you have a constant of variation, and in this case is my constant, when my constant of variation is the number of days worked, then the number of men and the number of blocks have a direct relationship, meaning when one increases, the other decreases. And you can set up a mathematical formula for that. Right? When I keep the number of blocks constant over here, this was when the blocks was constant. Blocks constant. When the number of blocks was constant, I wanted to reach 100 blocks. Then the men and the days had an inverse variation, because if I increase the men, it's going to take less days to make that same number of blocks. While if I decrease the men, I'm taking more days, and if I increase the men, I'm taking less days. So in that case, the men and the days would have an inverse variation, and you can set up a mathematical formula. So basically, that is what is happening in inverse and direct variation. There are some quantities that, in some sense, they will relate in a direct way to each other, meaning when one increases, the other increases as well. And then there are quantities such that they relate with each other in a way that they have what we call an inverse variation. When one decreases, the other decreases. But there must always be some constant, something constant. And everything now can be represented mathematically. That's what inverse and direct and inverse variation is all about. So let's go straight into it and keep it simple. I just gave it as an example so you can see what something in real life that you can relate to, and it's now putting mathematics to it. All right, so somebody who running the business can maybe set up a little formula that says, okay, when I have 10 men, the number of blocks I produce is 10 blocks, or say 100 blocks. And therefore, if I have now 20 men, then I expect to have 200 blocks. A simple formula like that, double. It don't have to be double, but it can be some other factor. Right? But they can actually set up a mathematical formula to work it out to say, okay, if I want to do a certain number of blocks in a certain number of days, how many men do I need? And they can set up a direct or inverse variation formula to do the calculation. Right? And you usually have some prior knowledge about the rate of production or the rate of work or how the two variables relate to each other. And that's what the questions are set up. But let us get into it now. So let's look at direct variations first. Direct variation. If two variables, I'm using x and y in this class, I just use men and days and blocks. Could be anything. I'm using x and y for the purpose of the class and for the purpose of introducing this thing. If two variables x and y are related in such a way that when x increases, y also increases, and when x decreases, y also decreases, then those two variables are said to be obeying a direct variation. They are said to be obeying a direct variation. So the word direct means that when one increases, the other increases. When one decreases, the other decreases. All right? When that is the case, there are certain ways that the exam question will be written. There are certain phrases that they'll use. And for example, they say y varies directly as x. The keyword always is directly. Directly. They might also say y is directly proportional to x. That's another way they might put it. So one of those two ways they must say. So y varies directly as x, or y is directly proportional to x. All right. The mathematical symbol for that, y is directly proportional to x, is this. And this is a mathematical formula when you have a direct variation. Y is equal to some constant of variation times x. That's the formula when you have a direct variation between two variables. Where k now, k is that variation constant. So just like when we were doing the example a while ago, I say, okay, what if we keep the number of days constant in one sense? What would happen? What would be the variation? This k now is like that quantity that you're keeping constant. All right. And when you're doing variations question, tell you from now, when you're doing variations question, right, your aim primarily, your first aim always is to find the k value, the constant of variation. All right, constant of variation. We'll go straight into an example. You'll see. So look at this example now. Given that y is directly proportional to x, and y equals 10 when x equals 2.5. So they will always give you some condition for you to use to find your k. Find k. They'll always give you some known information that you can use to find your k. Always. Right? It says now, determine the value of x when y is 20. That is part A. And determine the value of y when x is 1.5. Now, the first thing you want to do when you have a variation statement is write your variation expression. So the first step is always to find k. Right? That's always what you want to do first, find k. But you have to write your variation statement. You write a variation statement. That is what they said. So this is a mathematical representation for what they said up here. That y is directly proportional to x. That's a mathematical statement for that. All right? That's a mathematical statement for that. Y is directly proportional to x. All right? And then now, sometimes you don't need to write this too, sometimes you actually don't need to write that, right? You can go straight and just write the mathematical formula for the variation, right? Which then becomes oh, which then becomes that. You write the variation equation by introducing a constant k. So you can just write that y equals a constant times x. Y equals a constant times x. So when it's a direct variation, y equals a constant. One variable equals a constant times the next variable when it's direct. All right. And what you do next now is that you use the known values that they gave us. The y equals 10 and x equals 2.5 up the top there to find the k. That's what you do next. Find the k. So you find it, you put them in the formula. You put the y and the k value in this formula right here. All right, you put them in the formula, and that is for you to find the k. So hope you can see. It can give me some problems here. Let me see if I can get back the pen. All right, it's here. So you put these two values in this formula, and that is what we get. So y equals 10, and the x is 2.5. And then when you divide by the 2.5 here, you see that the k equals 4. Now the k is a constant and it's not going to change. So because the k is a constant, it means that this formula is really y equals 4x. And that is now your known relationship formula. That's the relationship, right? Now that you know the k is 4, that is really your formula, y equals 4x. And then now, once you have that, you write the relationship formula, which is y equals 4x, as I've said. And then you use this formula now to answer this question up here and to answer that question up here. That's what you do next. All right? That's what you do next. So you use a formula to answer the questions. First one, when x equals 20, right? You put the 20 right here for the y. When y equals 20, sorry, you put the y equals 20 in the formula. Put the 20 for y in the formula. That's what I did right here. And it means that the x equals 5. And then in part B, the x is 1.5 now. In part B, the x is 1.5. So you put the 1.5 for the x value right there. And the calculation tells you that the y in that case is 6. Y in that case is 6. All right, we're going to do an example or two after this. It's very easy, trust me. Very, very easy. Right, so if you're not seeing it fully so far, no problem. I'm going to do a couple of examples and you see. But let's look at inverse variation. So remember, the direct one now is time. So if I, for example, say that P is directly proportional to Q squared. Suppose I say P is directly proportional to Q squared. Then I have to write P equals a constant times Q squared. Like that. That is it. And this is my constant of variation. All right. Let's look at the inverse one now. Inverse variation. So the inverse variation now is what one where one quantity increases, the other quantity decreases, as we did with the men and the blocks. No, the men and the days. All right. So that's what this is about. If two variables x and y are related in such variables x and y are related in such a way that when x increases, y decreases, and when x decreases, y increases, then they are obeying what we call an inverse variation. And when they obey an inverse variation, some of the things we can say is that y varies inversely as x. So this is the word that you're looking for now, inversely. Or they might say y is inversely proportional to x. That's another way they might say it in the question. Y is inversely proportional to x. All right. And in that case, that is what you write now, the inverse. All right. So y is proportional to 1 over x. So when it's inverse, is now y is proportional to 1 over x. In that case, now y is equal to a constant times 1 over x. Or we can just write y equals k over x. This is for the inverse variation. This is inverse. Simple as that. For the direct, y equals k times x when it's direct. And y equals k over x when it's inverse. As simple as that. And you're trying to find k first using the known x and y values. Simple as that. K is a constant of variation, or what we call a variation constant, or the constant of proportionality. Same thing. All right, we want to see some of these phrases when we start practicing a couple questions. All right, look at this example now. Given that y is inversely proportional to x and y equals 3 when x equals 10. Remember now that this information right here always give you a known set of values to find k, to find k. All right, and this is it now. This is it now. So same procedure as a derivation. But can you hear me?
Yes, sir.
Yes, sir.
Oh, good. All right. So then that's it. Y becomes k over x. This is what you basically end up with. And sometimes it becomes useful to write it like this by simply multiplying the y x over here. All right. So sometimes it becomes convenient to write it like that. But this is what you end up with primarily because of the inverse variation. All right. And then what you do now, you're trying to find the k first by using the xy value that they gave you. Y equals 3 and x equals 6. Right? So you put them in the formula. So you put those two values in this formula right here now. It tells you that the k is 18. And since k is 18, it's not going to change. K is a constant. You can write back the equation now with the k value. See, I write back this equation now. Right here with the k value. And now this is my formula now going forward. This is the relationship between x and y. xy will always be equal to 18. The product is 18 between x and y, right? Because an inverse variation. And then now I use this formula now to answer this question and to answer this question up here. So first one, I put in when y equals 6. If I put y equals 6 in the formula, then the x is going to be 3. It is pretty obvious. The second case, if the x is 1.5, put the 1.5 in the formula, and y is equal to 18. The y is equal to 12, sorry. Right? Because the 1.5 times y is equal to 18, you divide by the 1.5, and the y is equal to 12. All right, that's how it goes. And let me do a question. Let me do a question so we can see this thing. So we're gonna do the homework. We're gonna do the homework. We're gonna do the variations questions homework right here on this page. All right, try these questions for me for homework. I'm gonna do that one example, maybe two of them. They're very easy, they're really very easy. Right, but let me look at the one on the slide here. Let me look at this one. So this question says y varies inversely as x squared. So let me do this one. Let's do this one. Let's do this one right over here. I'll show you it very easy. So this question says, given that y varies inversely as x squared, use the values of x and y in the table to calculate the value of a and the value of b. All right, and in the table, this right here is a known pair of values that you're going to use to find the key. Always will give you a known pair of values. But they give you the question in words or they give it to you in a table. All right, this one they put the relationship in a table. All right, let's look at the solution over here now. All right, see here now, y varies inversely as x squared. What that means is that y is equal to a constant over x squared, because it said inversely, and it's y and x squared are the two variables. So because it's inversely, is y equals k divided by x squared. And it is convenient to just multiply the x squared up here. So I'm going to say, okay, the k equals x squared times y. And as always, find k first. I'm trying to find out what the formula is fully, you know. So you find k first. Always find the k first. What do you use to find the k first? You use the fact that when x equals 2, y equals 4. That's what they gave us right here. Right? That's what you use. Put them in this formula. Right? So you say therefore 2 squared times 4 is equal to k. But understand that because x is 2. Now this is 4 and this is 4. 4 4 is 16. So again, so therefore k equals 16. Now that the k equals 16, this formula becomes x squared y equals 16. This now is a formula that's going to use to find everything else that you want now. All right? So that is the formula now. This is what we call a relationship formula. If you look in the table now, right here first, I'm going to use this formula right here first. When x equals 5, y equals a, put those two values in that formula. When you put those two values in that formula, you get 5 squared a equals 16. 5 squared times a equals 16. And the 5 squared is 25, so that's 25a equals 16. So a equals 16 over 25, done. And in the other case, using here now, right there, put them in a formula again. It says when x equals b, y equals 0.25 or a quarter. Put the two of them in the formula, right? So it means that b squared times 0.25 is equal to 16. That's what it means, you know. B squared, which is the y squared, no, the x squared, sorry, times the y, which is 0.25, is now equal to 16. So you're going to divide by this 0.25. All right, so you're going to get b squared equals 16 over 0.25, which works out to be 64. And then if b squared equals 64, then the b equals the square root of 64. The b is equal to 8. That's 16, 64. 64. And that's it. So we have found the value of A, we have found the value of B, but we have to find K first. Now, some variations question will actually ask you for the value of K, while some of them will not even mention any K. Right? But whether the question asks for a K value or not, that's the method I wanted to use, where you find K first. Always find your K values first. And after you find a K value, you can write a relationship formula. And then from the relationship formula, you can find the values that you want to find. Let's do one more example before we finish. One more example. You can call it a day. So we did an inverse variation one a while ago. Let's look for a direct variation one. Right here. Let's look for a direct variation example. Here. This can says two variables x and y related such that y varies inversely. That one is inverse. So I'll leave that one for you to do as homework. Let's look at one over here. All right, let's do this one right here. Let's do this one. Just for practice. This one. We don't want to do the one that doesn't find the K, but there's no problem. Table of All right, let's do this bottom one down here. Let's do this one instead. This one. And this one asks you to find K. Okay, let's look at this one. That one. All right. I never finished for the day. I'm gonna see that it's the same procedure basically. Very easy stuff, believe me. All right. So this question says the incomplete table below shows one pair of A and R, where R is directly, the word you know, keyword is directly proportional to the square of R. Square of R is R squared, you know. That's what the square of R means, R squared. So A is directly proportional to the square of R. So the first question there, first question is asking us, the first question right here is asking us to express A in terms of R and a constant K. So you see some question asks you to do that. So that first statement is that the A is equal to a constant times R squared. As I said, directly proportional to the square of R. Square of R is R squared. So that's your formula. A is equal to a constant times R squared because they said directly. If that said inversely, you'd have to write A equals 1, not 1, K over R squared. If that said inversely, it would be A equals K over R squared. But because the question said directly, it is this one. Directly is when you multiply by the K. Simple as that. Part 2 says that to calculate a constant. Some questions ask for a constant, some questions don't. Look at this example right here. For example, they don't ask for no constant. It's the same sort of thing. Right? They don't ask for any constant. Right? This question up here talk about a constant as well. So some questions talk about constants. One here, this one asks for a constant to see there. Right there, so this one don't mention no constant. Right? This one don't mention no constant. So it depends, right? It varies how they ask these questions. But it's the same concept, same approach, same principle. All right. So second part now ask us for a constant. Now whether they ask for a constant or not, that's what you have to do next anyway. Find a constant first. So I'm still gonna say find constant first, so we can remember. Find K first. What do you use to find K? The known pair of XY values and a known pair of values that they give you for the two variables, which is right here. Use this known pair to find K. That's what you do, right? And that known pair is that A equals 36 when the R equals 3. Put them in that formula that you have there, right? So put them in this. So you're gonna say, all right, 36 equals K times 3 squared. Hope you understand that because the A is 36, see there? And the R is 3, see it there, right? Let's put them in the formula right there. And we're trying to find the K. So the 3 squared here is 9. So it means that 36 equals K times 9. And now we don't know how to find the K. Divide by the 9. So means that the K is actually equal to 4, which is 36 over 9. Therefore, the K equals 4. That's the answer for part 2 in this question. In some other questions, you just need it without them asking you for it. And the last part now is asking to complete the table. To complete the table, we need to find the value here and the value there. Let's give those values letters so we can reference it. Let's say that this value is small a, and this value is, let's say that this value is small a, and this value is small r. So we can reference them. All right, so let's go now. Part 3. Oh, we're not finished yet. Now that we have that, we're going to write the relationship formula. So this relationship formula, now that we know the key, that relationship formula becomes that A equals 4 times R squared. This formula now governs everything going forward. You now know the relationship fully between A and R. So already know. Part 3 now. I'm using the formula. In the first case, right, the A equals small a and the R equals 5. That's right here. A equals small a and the R equals 5. Right? Put those values in the formula. So you put those values in the formula, you're going to see that the A is small a equals 4 times the R is 5, so you get 5 squared. So the small a is equal to 4 times 25, and 4 times 25 is 100. So the a is 100. So therefore you could put 100 in the table right here. 100, this is 100. And they use the same formula again now for this side. For the R, the small r, and you look at the table. When the A is 196, the R is small r. The R, capital R, is small r. Like that. Put them in the formula. So the 196, which is the A, is now equal to 4 times R squared, which is a small r squared. What is that? But understand that? About with me?
Yes, sir.
All right. And then.
No, sir.
Huh?
I understand.
You don't understand?
No, sir.
Why you don't understand?
Same part the way it does, sir.
All right. All I did. You understand this formula right here, so now? This one. That the A
No,
is now
sir.
equal
I
to.
understand the formula neither.
All right. The A, that is 4R squared, because remember we started with this, you know.
Yes, sir.
Started with that. And we worked out that the K is 4. So I would always take the K for 4 and put it right there, so. And that's how we get this. The K equal 4 there, so now. That is now the formula. So that is the formula now. The A is just equal to 4R squared. Because we now know that the K equals 4. How we know that the K equals 4? Because we put these values in this. You see this? We got this from a statement that A is directly proportional to the square of R. The square of R means R squared. And the statement was that A is directly proportional to the square of R. If a question says y is directly proportional to x, then you write y equals kx. If the question says p is directly proportional to q, you write p equals k times q. If the question says m is directly proportional to n, you write m equals k times n. Once it says directly, the first thing equals k times the second thing. It's as simple as that. So since this question said A is directly proportional to the square of R, square of R simply means R squared. You know? So you could have said A is directly proportional to R squared. That is why we wrote this. A is directly proportional to R squared, so A is equal to K times R squared. And then you use this pair of values that they gave you in the table right here. You use this pair of values that they give you to find the K value. They will always give you a pair of known values to find the K. So you put them in there. So the A is 36 times K and the R is 3. So you write 3 squared. 3 squared is 9. Right? And so the K must be 4, because 4 times 9 is 36. So the K is 4. That is the K. K is 4. Now that you know that the K is 4, you put by the 4 right there for the K. That's how we get this. This right here. So you put by the K for the 4 now. The K is a constant, it's not going to change. So once you use this known pair over here to find the K, that K will never change again. It is called a constant. It's not changing. The A is changing and the R is changing. The K is a constant, it's not changing. So because you know the K, you can now write this formula that we have right here. So This formula. Now that we have that formula, that formula will work in this box and will also work in this box. And the question is asking us to fill out the table for here, put the value in there, and put the value inside here. This value is a A value, and this value is a R value. This value that we don't know is the A value when the R value is 5. This value is the R value when the A value is 96. That is all. Right? So what I did to reference it, I call them letters. So I call this value A, I don't know what it is, and I call this value R. So what are the pairs of values? The pairs of values for this one, for this point, is A equals A and R equals 5. That's what I use right here. Right here. And I use them in this formula. That formula governs everything else. That's why I did my calculation down here. So let's look at it. Let's look at it. The A is small a and the R is 5. So the A is small a, see there? And the R is 5, see there? R is 5. R is 5. So I put them there. And then the mathematics tell me that the A works out in that case. A works out to 100. But the other pair, which is this pair now, the A is 196 and the capital R, I'm going to call it common R, just so I can reference it. That's what I put right here now. Right here. The A is 96. And the capital R, I'm just call it common R. I'm going to call it anything more. I'm going to call it X, Y, anything. I'm just call it common R. So I'm going to put them values here now in that formula. How am I put them in the formula? The A is 96. So this is 96. Doesn't write this up. See, the A is 96. The 4 come back here, so see there? The 4 come back here, so. And the R is small r. So this R is small r. That's that. So I'm going to put a formula there. I'm going to put an equation here to solve for R. So I'm solving that for R now. It's straight substitution. There's nothing magical to it. It's just substituting values. Right? The main thing is to know that this statement that I said, A is directly proportional to R squared, means that A is equal to a constant times R squared. And then use this formula, use these values to find the K. Use these values to find the K. By plugging these values inside here, inside this, to find the K. Put the A equals 36 and the R equals 3 inside here, and you work out the K. And when you know the K, you just put the K in the same formula now. And you know the K is 4, so you replace this K with 4. That's what I did right here. So replace the K with 4, right? Because I now know that the K is 4. And then this is my relationship formula now. This formula now governs everything after that. So plug the values in that formula. The values in the table, plug them in that formula. And the formula tells me what the unknown values are. Understand that?
Yes, sir.
Right. So now I divide by this 4. I divide by this 4. This becomes 49 equals R squared. And everybody knows that 7 squared is 49. So you can say therefore R equals 7. So in my table over here, let me erase all of this again. Let me erase all of this. But what is important? This is what you use to find a K. I call this small a, which will work out as 100. I call this small r, which will work out as 7. That's that. That is it. All right, go back and look over the video again, guys. That's the beauty about doing online class. You can go back and look at the video. All right, if you're still not sure, you just give me a shout. All right, just give me a shout.
Sir, excuse me,
Yeah.
sir. Before you go, so you're saying that in every one of these tables, sir, there would be that constant set like 30.
Always give you a pair of values that you know. Look at all of them. They'll always give you a pair of values to find your key. Look at this one. See this one here? This is what you're going to use to find the key. All right, let's look at the next
Yes,
one.
sir.
That'll give you a statement. See here? Then give you the known y and the known x. That is what you're going to use to find the key. They'll always give you a pair of known x and y values to find the key. So in this example here, just put the yes up for the 50, for the y, the k, and put this for the 10. So you get 10 squared. See that? And you
Yes,
find
sir.
the k equals 100, so the k equals a half. So they will always give you a pair of x and y values, or the two variables that you know. Let's look at the next one. See that also? See the pair also? For this one, see the pair there? See there? They'll always give you a pair. Next one, see the pair here? They'll always give you a pair of values to find the k. Look at this one. See the pair here? That is the pair. See look at this question. So this question, see there, they say and S equal 8 when R equals 3. That's a pair. They will always give you a pair of values to find the k. Some question will mention k, some question won't mention any k. But remember, if it's direct, is the first thing. If it's direct, the question said direct variation. Then is the first quantity, first thing. Let's write it out. The first thing equals k times the second thing. Simple as that. If it's inverse, if it's an inverse variation, inverse, then the first thing equals k divided by the second thing. And then you use the known pair to find the k. Use the known pair to find the k. Use the known pair to find the k. Find the k first. See there? There's always a known pair. So the known pair here, they put it in writing this time. Known pair. Every one of these variations question, they have to give you a known pair of values to find your k. Understand? That's how these questions go. They're not difficult at all, at all, at all. Just know that direct means times and inverse means divide. Direct means k times, inverse means k divided. Inverse, direct, k times. Inverse, k divided. Inverse means 1 over, you know? 1 over. Let me show you an example for direct. Give you an example, show the common sense of it. Watch this now. You may say y is direct proportional to x, right? Or y is inverse proportional to x, inverse. So y is equal to k over x. It means that x times y equals a constant. Now watch this now. Suppose me do some math, right? Then give me some values, right? I'm a constant work out to. So I'm a constant work out to 100. So then give me some values. So someone say when x equal 10, y equal 10. So put them tell me that as my known pair. It means that 10 times 10 would equal to k. So k would equal to 100, right? So it means that my formula would really be that xy equals 100. Remember this is inverse, you know. But this was inverse, you know. Inverse variation. Inverse. We call inverse for 2 now. When x are 1, what y I forgot be for the answer to be 100? Tell me. Tell me now. 1
100.
times 100. When x are 2, well, y I forgot be
50, sir.
50. You see? So the x going up, the y coming down. When x are 4, well, y I forgot be
25, sir.
5. When x are 5, well, y I forgot be
20, sir.
20. You see that? That's an inverse variation. When x are increase, When x is increasing in value, y is decreasing in value. That's an inverse variation. Right? Look up on a direct now. Suppose them said direct. That's what's inverse a while ago. Suppose them said direct. All right. So y equal k times x. All right. And let's say them give me a pair of values now. All right. So suppose them say y equals 200 when x equals 2. That's a simple value. What I do? Put all my known pair of values. Put my known pair of values in the formula. That tells me that 200 is the y equal k times 2. Don't it? So it means say k equal 100 again, don't it? I just use another example. This one now is direct. Direct. Show you how it works. Direct. So the k equals 1. Can be divided by the 2. I see the k equals 100, right? So k equals 100. K equals 100. Now that we know that k equals 100, the formula here now is that y equal 100 times x. Y equals 100 times x. Let's look at it now. It's a direct, you know. Watch this now. If x equals 1, if x equals 1, where y equal? Where y equal? 100, see there? 100 times 1 is 100. If x equals 2, instead of multiply by 100, you know, where y equal?
50, sir.
No, man, you're multiplying them. It's 100 times x.
My was 200.
200. When x equals 3, instead of multiply by 100, where y equal?
300.
300. When x equals 4, you still have to multiply by 100, you know, to get the y value, you know. Where y equal?
400.
So you see that as the x value increases, the y value increases. As the x value increases, the y value increases. That's a direct variation. That's how it works. The mathematics work out itself. So direct variation is always k times. Inverse variation is always k divided. And you see the numbers show you. The numbers show you. It's a relationship between them. Alright? But let's go and practice it. Try these questions over here. We're going to work them out on Wednesday before we do the classwork. Right? We're going to work them out on Wednesday. Some of them do the classwork. And you see that it's really very easy. Trust me, it's one of the easiest. Right? Once you write a statement, find k first. Use a known pair of values to find k first. That is all. The question that I did as my examples, I want you to go and do them yourself. Do those questions yourself first. Right? Do the very same questions yourself. Just try them yourself first. Do them yourself. Go back at the video if you have to. Try it 2-3 times yourself first. Right? And then now you see that these questions over here are really very easy. One of the easiest things in maths, believe me. Direct and inverse variation. One of the easiest. You basically just substituting values. You're substituting values, that is all. The only calculation you do really, well, you calculate the value of k, and after you find the value of k, you put the k value in the formula. Because the k not changing. Once you get the k is constant, you know, constant means not changing, you know. The other values are called variables, they vary. That's why they are called variables, they change value. But a constant is a constant, and they'll always give you a known pair of values to find your k. Some questions will ask you for the k, some questions will not ask you for the k. You still have to find k first. Regardless of how the question set up, find k first, put the k value in the formula, and then when you know the formula fully know, you use that formula to plug in values to find what you don't know. That is all. So question, most times they give the question in the form of a table, like these. If you notice, most of these are like tables. How many of them? 1, 2, 3, 4, 5, 6, 7. Out of the 7 of them, 5 of them are tables. 2 of them are wording. Mostly, you know, not no table. Most of these questions they give you some kind of table. Easy like cheese, man. Trust me. Easy. Easy. Right? You just need to know how to just write the relationship. Direct means the first thing times the second thing. Inverse means the first thing The first thing, direct means the first thing equals k times the second thing. Inverse means the first thing equals k divided by the second thing. And those are sometimes they might say the square of x. The square of x just means x squared. Or they might say the square root of x. You put the square root over the x. Or they might say the cube of x. Cube of x just means x cubed. Something like that. Right? But it's a first variable and a second variable, and you have a constant. If it's direct, it's a constant times the second variable. If it's the inverse, it's constant divided by the second thing that is varied. All right, and they use the known values that they give you. They will always give you a known pair of values for you to use to find the k. Whether the question asks for a k value or it does not ask for a k value, you still have to work out a k value. And you put the k value where you work out in the formula that you write first. And when you put the k value in the formula and you know the formula fully now, you use that fully formula that you now have to work out the unknown values. Unknown values. By putting, they give you one known value and one unknown value. Put the known value in the formula to work out what the unknown value is. And they'll give you another pair. One value known, the other value don't know. The unknown. Put the known value and the formula tell you what the unknown value is. Easy, man. Substitution. Trust me. I think I'm spending too much time talking about this. The way it's easy. Just go home and do the two examples that I did first. Do the two examples that I did first as homework. And then you try the rest of them on this page. All right? It's very easy. Believe me. All right? So we're going to end it there today. All right? We're going to end it there. So see you guys on Wednesday. Remember, link me if you have any issues. All right? Okay, guys?
Yes,
Yes,
sir.
sir.
All right, then. So, bye.
Bye.
Yeah.
Okay.
Bye, Dad.
Bye, princess.